All right. So the calorimeter is a vessel that you can monitor the initial and final temperatures and all that. But the process of doing that is called calorimetry. So we're going to do a calorimetry example where what we're looking for is either the specific heat capacity, the heat capacity, or Q. And if you remember, we already have a relationship between that, right? Specific heat capacity is here. And that is Q divided by the mass times the change in temperature. The heat capacity is just Q over the change in temperature. We've already talked about that. And then there's another more specialized calculation, which is the molar heat capacity, where it's just Q times the number of moles over, I'm sorry, Q divided by the number of moles over the change in temperature. So it's moles are substituted for grams in this case for molar heat capacity, but we're not going to talk much about that. We know the manipulations, right? How to get to any one of those three terms. If we have this as our starting point, the specific heat is Q divided by mass times the change in temperature. We can manipulate that and solve for anything. So the main manipulation is going to be here, right? Because sometimes, most of the times, you'll be given a specific heat capacity and the mass and the change in temperature, but you'll have to find Q. All right. So with calorimetry, we can find specific heat capacity. We can find that. And this is an example. It says a piece of copper with a mass of 19 grams was heated to 87.4 degrees Celsius and then placed in a calorimeter that consisted of 55 grams of water at 18.3 degrees Celsius. And it says the temperature of the water rose. So this is your delta T right here. Started at 18.3, went up to 20.4. What is the specific heat capacity of copper, right? And so here, we're going to say that these two have to be equivalent. The specific heat capacity of copper and water are equivalent because the heat that's gained by the water is the same as the heat that's lost by copper. So the Q value is going to be equal. So if the Q's are equal, right? So right here, Q water and Q copper are going to be the same because, again, this is two bodies transferring heat. One is higher temperature, the other one is lower temperature, and then they equilibrate to the same temperature. So if the Q's are the same, then we can set the two equations equal to one another. And in doing that, we could solve for the specific, the specific heat of copper. All right, so that's just a manipulation of this, which you see right here. So you have the specific heat of water times the mass of water times the change in temperature of water divided by the specific heat of copper times the change in temperature in copper. So copper, you see, has a different temperature change, right? It was heated to 87.4. And the final temperature is the same in this case. So it's 20.4, right? And then 18.3 is the starting temperature for water. So the change in temperature for water is here, 2.1 degrees Celsius. And then the change in temperature for copper is here. All right, so 69.1 degrees Celsius. All right, so the water started at 18.3 and rose to 20.4. The copper started at 87.4 and ended up at 18.3, right? So the change in temperature for each one is different. That's it. The rest of it is just knowing the values for specific heat. And this is a known value. For water, it's 4.18 joules per degree Celsius grams. And then for copper, that's what we're solving for. So once you put these numbers in, then the specific heat of copper is here, 0.38 joules per degree Celsius per joules per degree Celsius times grams, right? So anytime you're given a calorimetry problem like this, normally you're either going to be solving for the specific heat or the change in temperature for one or the other. But the key is to understand is right here. The key is here, right? The way you set it up, when you add in that, when you add in the hot copper to the calorimeter, the Q that's given off, or the heat that's given off from the copper, is the same as the heat that's gained for the water. And so that is the relationship that allows us to set up the two specific heat equations equal to one another, and then solve for the other. All right. Questions about this? So this is again dealing with enthalpy and calorimetry. So now we're using calorimetry is the tool that we use to study enthalpy, or temperature change, or heat transfer. All right. All right, let's do one more dealing with specific heat and heat transfer. And here it says using specific heat capacity, potassium perchlorate is used as an oxidizer in fireworks. How much energy in joules? So this is what it's asking for. How much energy in joules is required to raise the temperature of 10 grams, so that's my mass, from 20 to 900, right? So that is, again, what we're looking for is the Q value. And if we know this equation, we can manipulate it to find Q. So Q is this: specific heat times the mass times the change in temperature. And the units are here, right? So delta T, I'm sorry, units are here. It's either going to be in joules or kilojoules. So delta T is here, 880. We get that from subtracting T final minus T initial. T final is 900. T initial is 20. So we subtract those numbers to get delta T, which is 880. And then we have our specific heat. This is a known value, right? You can look that value up. There's a table that I'm going to give you that has the different specific heats. There's a table in the book. Regardless of which book you're using, there's a table of specific heats there as well. So that's a known value. And then we have a mass of 10 grams. So all we're doing is calculating that amount. And what we get is 7,096 joules, or we can write this as 7.1 kilojoules. All right, any questions about those two examples? All right, so we can find specific heat using a calorimeter if we add in some hot body and it transfers heat to a body at lower temperature. We can say that the two Qs are equal, right? So when we do a heat transfer like this, when we add something to a calorimeter, then we can say that the two Qs are equal, and we can solve for a specific heat of either one. We could also solve for Q using specific heat, which we've already done. And then we can also look at the enthalpy for a reaction. Let's talk about that now. So let me move to that section. I'm not going to do this problem right here, because it's similar to the one we just did. We're going to talk about now enthalpy as it relates to a specific reaction. Right, so we've already talked about exothermic, endothermic. We've already talked about how when reactions happen, they either absorb heat or they release heat. And so with that being said, we've already talked about the thermochemical equation, how to write that. The way you write it is to first balance the equation, and then go in and calculate the delta H using Q, right? That's how we're able to calculate that. And we did that with an example the other day. The notes that I had from that, for some reason, didn't load, but we did calculate that the other day. Then you just go back and write out the equation with the energy either released or absorbed shown as delta H for that reaction. Right? So when we talk about reaction enthalpy, it is defined as the change in enthalpy per mole of a species. Right? So we can look specifically at a reactant in a molecule, in a reaction, and determine what the enthalpy for the reaction is, right? And it is this. It's the energy or the heat given off per mole at constant pressure. So and this is not DHR, it's delta H. And a lot of times you'll see this written as delta H reaction with the RXN subscripted, right? Notice when we're calculating the delta H for a reaction, it's really calculating Q first and then calculating the number of moles. It is going to be based on, in most cases, the limiting reactant. All right, so we're going to base the delta H for the reaction on the limiting reactant. So let me write that down here. So it's based on the limiting reactant. All right, and one of the things about this, about the enthalpy of a reaction, is that it is what we call a state function. It's a state function. So it's dependent on the conditions. It's dependent on the temperature, the amount, the pressure, all of that. So it's an extensive property. So it's dependent on the temperature, sample size, etc. Pressure, right? So for this example, what you have here, you notice, I want to show you something else too. This is the same reaction, but if you notice, the coefficients in the second reaction are double, right? Everything is multiplied by 2.
Dr. Russell,
Go ahead.
we can't see your screen anymore.
Oh, shucks. Sorry. Hold up.
You're fine.
Thanks for letting me know.
Yes, sir.
If it does it again, just say so, because I'm running this from my iPad. Sometimes when the iPad gets overheated, that happens. I don't want to fool with my laptop today because it's been letting me down. You can see it now though, right?
It just says you're screen sharing, but it's okay. There we go. It's coming now.
All right. So with that, like I said, these two reactions, let me put a arrow in here. These two reactions are the same, but the coefficients are double than the second one. So notice what happens. If I double the amounts, then I'm also doubling the heat given off, because it's a state function. So if the heat given off is going to be based on the sample size. Think about it like if I got, let's think about the previous example with the fireworks. If I have a skyrocket that has 10 grams of potassium perchlorate, and I have another one with 20 grams, the one with 20 grams is going to give off more heat, right? Because the heat given off and the enthalpy, that's a state function. So it's dependent on the size of the sample as well as the temperature and all of that. All right, so let's look at an example of how we apply this and look at how we can calculate delta H for a reaction. So we have an example here. We're going to walk through it. All right, so it says when 2.31 grams of phosphorus, so it's giving us the amount of phosphorus in grams, reacts with excess Cl2. So again, when we calculate delta H for a reaction, a given reaction is going to be based on the limiting reagent or the limiting reactant. It's not based on if one is excess and one is limiting, it's not going to be based on the excess because that's going to change the number, right? It's a state function. It's based on excess, then the heat is going to obviously be more. The heat given off is going to be more, all right? Or absorbed is going to be more. So we're going to look at this. It says 2.31 grams of phosphorus. It gives the molar mass on purpose, right? Because we're starting in grams, but we're going to need moles. So it gives us the molar mass. Reacts with excess Cl2 gas to form PCl3 and a calorimeter. And it says the specific heat capacity is 2.16 kilojoules per degree Celsius. So it's giving me heat capacity. All right. And it says the temperature rises by 11.06 degrees Celsius. So all of my terms are now given to find Q. I got delta T. I have specific heat capacity, and I have mass. So I can find Q, right? That's the first thing we need to do for a problem like this. Because if we're finding delta H of a reaction, that means that is the heat given off per mole of a reactant, all right? And we did, when we were first writing the thermochemical equations, it's the same thing. All right, so we need to find Q. So that's this. We're going to just take this and rearrange it. Right, so here is the rearrangement to find Q. Right, it gave us the heat capacity, not specific heat. Let me take that back. It's not specific, it's just heat capacity. So it just gave us C. But even with that, we can find Q. All we need to do is rearrange the heat capacity equation, which I have highlighted, right? And the calorimeter and the reaction heat capacity are the same in this particular case. As long as the pressure is constant, you can make that assumption, right? So we can find Q with the heat capacity, and it gave us the heat capacity, which is this number right here. We can say 2160 joules per degree Celsius. And then it gave us the temperature change, which is 11.06 degrees Celsius. Obviously, degrees Celsius will cancel, and we're left with this number right here for Q. All right. Now, to find delta H of the reaction, and let me put that in here. It's the Q per mole of a substance, right? And if we look at the equation, we see, and we're looking at phosphorus because that's the limiting reactant. We have Q, which is 23.8 kilojoules or 23,800 joules, however you want to do it. And then we know that this number we get from where? Where do we get the number of moles of phosphorus from? What information did it give us at the very beginning that would allow us to calculate moles of phosphorus? Wouldn't that be just grams over molar mass of phosphorus? Isn't that right? It gave us 2.31 grams. It gave us a molar mass of 30.97 grams per mole. So from that number, we can calculate that it was 2.31 grams divided by 30.97 grams per mole. All right, so the grams are going to cancel, and that's where we get that 0.075 number from. All right, following? Anybody not following? All right, so that gives us this number here, 318.5 kilojoules per mole. That's how much heat is given off for phosphorus, right? But in the equation, the coefficient for phosphorus is 2. And so since this is a state function, we have to take that 2 and multiply the specific heat, the enthalpy that we calculated. We have to multiply it by 2 to get the correct number. So we're going to multiply . So since this is a state function, we have to multiply that value by 2. So we calculated 318.5 kilojoules per mole, but since the coefficient, the stoichiometric coefficient in the balanced equation is 2, we have to multiply that value by 2 to get the right number. So this is the correct number right here. All right. Any questions about that? And you can, this method, you can apply to any of these types of problems. Any problem that asks you about calculating delta H and writing the thermochemical equation, we can write this now. All we have to do now is go back and put this in because we know delta H of reaction. So that was the other part of the question. It said write the thermochemical equation. So we just go back and put this number in, 637 kilojoules per mole. So that equation shown with the heat that's either given off or absorbed, that's the thermochemical equation. All right. Why is it positive? What does that mean that that number is positive? What can we say about the reaction if the delta H is positive? Is it exothermic or endothermic? All right, if delta H is positive, it's endothermic. And the way you can tell that without knowing the number is right here, that the temperature went up. So that means that heat was absorbed by the system. If the temperature had gone down, that would mean that heat got released by the system. But because the temperature went up, that means that heat got absorbed. And so now you can say that the reaction is endothermic. Anytime delta H is positive, it's endothermic. If it's negative, it's exothermic. All right, any questions about any of the examples we just looked at? So we looked at the delta H for reaction, and we also looked at determining through calorimetry, and I'll take these other pages out, but we also looked at determining through calorimetry how to find the specific heat of either the body that was added to the calorimeter or the water that was in the calorimeter. So we can find either one depending on what the question is asking for. All right. One other topic. So we looked at calorimetry. We've looked at delta H for reaction and writing thermochemical equations. And so now we're going to talk about Hess's Law. And that's the last thing that we want to talk about today. This is going to take a minute to actually get through. And I'm not going to use the example that's in the PowerPoint because it's just too convoluted. So I'm just going to add a page.
Dr. Russell, it
Go ahead.
stopped sharing again.
Okay. Thank you.
Mm-hmm.
Don't feel like you interrupted me. I can hear your voice like, oh boy, I got to tell him again. But it's okay. And if it does again, just say something because there's no point in me talking about something you can't see. So
I was going to say, just so we can see the examples.
Yeah. Can you see it now? It should be back up.
It's coming, I imagine.
All right. Now, is it up?
It's there.
Okay, great. All right, so now we're going to talk about, I'm going to add this in. We're going to talk about Hess's Law. There's a lot of information on Hess's Law. Basically, the brass tacks of Hess's Law is this. Anytime a reaction happens, no matter how many steps it goes through to get to the product, the enthalpy for that reaction is just the sum of the enthalpies of each step. That's basically Hess's Law in a nutshell. So enthalpy, let me not say that. Let me say overall. So to go from reactant to product, if it takes 10 steps, the overall enthalpy is going to be the sum of the enthalpies for each step, whether they're negative or positive, whether the step is exothermic or endothermic. You're going to add up all the enthalpies at the end, and that's the delta H for the reaction. So delta H for the reaction is just the sum of everything. If it takes 10 steps, add the delta H's up for each step, and then that's the overall reaction enthalpy, right? And so it doesn't matter what Hess's Law is saying is that it doesn't matter what path the reactants take to get to products, right? Delta H is just the sum of all the steps. So let's say you have A going to B. But A also has to go through intermediates like C and D before getting to B. And each one of those is going to have a delta H. So that's delta H1, this is delta H2, and this is delta H3, right? So each one of those steps is going to have its own enthalpy. This is going to be, the overall enthalpy is going to be the sum of the 3 steps necessary to get to B. And that's all it's saying. And so with Hess's Law, it's kind of interesting because like a lot of the problems that you see dealing with Hess's Law give you like a process and then give you the overall way to get to that process. And part of the problem, or part of the intricacy of using Hess's Law is trying to figure out which processes to use to get to the product. So let's just jump in and do an example, and then we're going to explain every step. So let's say we have a reaction of methanol, and it's a combustion reaction. What's a type of combustion reaction? Going to formaldehyde. This looks like this. Same formaldehyde that they use in embalming fluid, plus hydrogen gas. That's a gas. This is a gas. I got a funny story about formaldehyde. I was working one summer at a computer plant in Huntsville, and one of the reagents that we used was formaldehyde to treat the circuit boards in one of the steps. And we had these big 55-gallon drums of formaldehyde in the back, and sometimes we have to refill the belt because it had these little sprayers on it that would spray different chemicals on the circuit board. And I knocked over a 55-gallon drum of formaldehyde, knocked it over, the whole thing. And thankfully I was strong enough to tip it back where it was supposed to be. But it still got all over the place. It had the whole building smelled up. And I tried to lie and say, I don't know what happened, but it was my fault. It was my fault. I didn't get fired though, but that's just one of those things. Anyway, so this is the reaction, and what we want to find out is what the delta H is. So normally, well, you could actually do this a couple of ways. You could compute it using computational chemistry, but you could also do it by performing certain experiments that give you either the products or the reactants from your initial reaction. So these are the experiments that were done. So you took 2 methanols plus 3 oxygens, and that gave you so for this experiment, delta H is negative 1353 kilojoules. All right. The other experiment, another experiment that was done was taking formaldehyde. Sorry about that. And then reacting that with oxygen.
It just stopped again.
All right. 1 second.
Mm-hmm.
Won't let me be great. That's okay. We're gonna make it work. When in the recording though, you'll see it. It won't be choppy. I'll make sure it's not.
Okay, great. Because that's the main thing I was probably like concerned about the recording.
I know how to edit. I'll make sure it's right. So delta H here is negative 520 kilojoules. And the last experiment was 2H2 plus O2, 2H2O. And the delta H here, negative 484 kilojoules. All right. So all of these experiments were done to give us a way to find out the delta H for that reaction. And so that's what Hess's law allows us to do. And you can see right here in this top reaction, that includes methanol as the start material. But we also need to include reactions that give us that have formaldehyde included, as well as water, because that's the overall reaction. I'm sorry, H2 gas. So we need to find reactions that include this. And the process for this is similar to like a redox. where you're going to end up adding reactions together to get a total reactions and canceling out things that are the same. So let's see what we got. We need this included. And we need this included. All right. And the stoichiometry's got to be the same. So all that matters. So you can see the top reaction includes methanol as a starting material, which is good. The second reaction has formaldehyde, but it's on the reactant side. That's fine. We can fix that. And then the bottom reaction includes hydrogen, but that's on the reactant side also. So we can fix, but all of that can be rectified. We can fix all of it. And I'm going to show you how. And what we have to end up doing is rearranging some of these equations, right? We're going to have to rearrange these two. So because what we want to do is add up everything on the left and everything on the right and end up here. Right? And it's a lot. It's a tedious process. That's why I saved it. All right. So with the first reaction, there's 2 methanols present, but we only need 1. So we're going to take this whole thing and multiply through by 1/2 to cut the amount of methanol. So this is 2CH3OH plus 3O2 going to 2CO2 plus 4H2O. All right, so we're going to take that, multiply everything by 1/2 because we only need 1 methanol. And we don't have a way to cancel that. So we just multiply everything by 1/2, including the enthalpy. All right, so that's going to also include delta H. We're going to cut that in half as well. All right, so this is going to be CH3OH plus, what did I have? 3 O2s. Yep. So 3/2 O2 going to CO2 plus 2 H2O. And that number, negative 1353, what is that divided by 2, somebody? It's going to be negative 600 and something. $676.5 or something like that. Is that right? So everything gets cut in half. So cut everything by 1/2. So that's we're going to use that equation. For the second one, we need this to be a product. So this one, the second equation, we need the H2 on the other side. So we need that on the other side. So what we're going to do for that one is reverse it. Sorry. Right, we're going to reverse that. So we're going to put the So we're going to reverse it to get H2 as a product. All right. So now what we're going to do here is put the water on this side. So 2H2O going to 2H2 plus O2. All right. When we do that, we also got to change the sign of the enthalpy. So instead of being negative 484, it's going to be positive 484. All right, so that's that. Now we got the H2 on the other side. And then for the final equation, we're gonna have to rearrange that one the same way. But then right here, we only need one of these based on the original equation. That's only one, right? So we want to multiply that by 1/2. So everything gets cut by 1/2. So this is gonna be this, including the enthalpy. So it's gonna be H2O going to H2 plus 1/2 O2. All right, and then the delta H is going to be 242. And it's still positive. Everything gets cut in half. All right, and then for the third equation, let's take that because we want the formaldehyde on the other side. We want that as a product as well. So we're going to flip that one around also. All right, so we're going to reverse this as well. And that is H2O plus CO2 going to O2 plus formaldehyde. Let's see, yeah. Right, that's fine because for the stoichiometry, everything is 1-to-1. So we don't have to touch that. All right. So now we're going to say, and the delta H for that was negative 520. And that's in kilojoules. All right. So now we have it set up to where we can add everything together. Right? We don't have to divide that third equation by 2. All right. So now let's see what we do. So now we can add it all together and then we can figure out what the delta H is. And this is the last step. And give me about another minute. We'll be done. So now we add it all together. So we take the first equation, 3/2 O2 goes to 1 CO2 plus 2 H2O. And then the second equation was 1 H2O going to 1 H2 plus 1/2 O2. Hold up, let me move that so you'll get confused. And then the third equation was H2O plus CO2 going to H2CO, which is the product that we're looking for, plus O2. So when you look at these two on this right side, when you add those two together, that's 3/2. Right, so we can cancel out the oxygens because that's 3/2 and that's 3/2. We can also cancel out the CO2s and we can cancel out the waters because we have we got an H2O here and one here, so that's 2 H2Os. So we can cancel those out as well. And what we're left with is our overall reaction, which is CH3OH going to H2CO plus H2. And then now the last thing to do is take all the enthalpies and add them up. So this is, for this step, delta H was negative 676, or I'm gonna say 677. For this second step, delta H was positive 242. And then for the last step, it was positive 520. So we add all those up It should come out to 86 kilojoules. And then, so that's using Hess's law. Now we've calculated the delta H for this reaction. But it's actually based on a combination of a bunch of different experiments where each one of those, the reactant and both products, the delta H for the reaction is measured or calculated. And then we go back and use those experimental data, add all the equations up, rearrange them when we have to in order to get that equation that we're looking for. And I know that was a lot in a short time, but I have a good video and I'm going to send you to reinforce this. And we're going to stop here because it's 10:54. So I apologize for going over, but I'll chop this video up and post it later. And that's going to be that. Go enjoy your break, all that good stuff. Eat some collard greens and stuff on Sunday. Yeah. Any questions before we depart?
Thank you.
Thank you. Have a good break.
Do the same. I'll see y'all back on Wednesday of next week. Whew, long time. That's all right. We're gonna make it work.